Welcome, engineers, to a crucial session that will transform how you manage system stability. Today, we're diving deep into building an intelligent alert processing pipeline, the brain of any robust monitoring system. Have you ever felt overwhelmed by alert noise, or worse, missed a critical incident amidst a flood of warnings? That's precisely the challenge we're tackling. By the end of this lesson, you won't just understand the concepts, you'll have a clear path to implementing a system that intelligently processes alerts, ensuring you focus on what truly matters. Our journey will cover several key learning objectives. First, you will learn about the alert lifecycle state management, understanding how alerts transition from new to acknowledged and finally to resolved. Next, we'll explore the design of a smart severity classification engine, moving beyond static thresholds to dynamic context-aware prioritization. You'll also discover the power of auto-resolution logic for transient issues, which drastically reduces alert fatigue. We'll cover essential manual acknowledgement workflows, ensuring accountability and efficient incident response. And finally, you'll grasp the importance of complete alert history tracking for continuous improvement and post-incident analysis. Let's begin building smarter, more resilient systems. Imagine being woken up at 3 a.m. by an alert only to find the issue resolved itself by the time you logged in, or missing a critical database failure because it was buried under hundreds of low-priority warnings. That's the reality many engineering teams face, and it's why intelligent alert processing matters. It's not about how many alerts your system generates, it's about how intelligently it processes them. Companies like PagerDuty and Datadog built billion-dollar businesses around this very concept. To achieve this, our pipeline is composed of four core interconnected components. First, the alert ingestion layer receives raw alerts, assigning unique identifiers and timestamps. Then, the severity classifier uses configurable rules to categorize alerts as critical, high, medium, or low based on metrics and historical patterns. The lifecycle manager tracks each alert's journey, maintaining state consistency from trigger to resolution. And finally, the auto-resolution engine intelligently closes alerts when conditions normalize, preventing alert fatigue while ensuring genuine issues remain visible. Together, these components transform raw data into actionable insights, making your monitoring system truly powerful. Every alert in our intelligent pipeline follows a predictable journey, a life cycle that ensures proper handling and accountability. An alert's journey begins as new with an assigned severity. This is its birth. When an engineer takes ownership, its status moves to acknowledged. This is a critical step for accountability. The alert is then moved to resolved, either automatically when conditions clear or manually by an engineer. Throughout this journey, a robust state machine prevents invalid transitions. You wouldn't want to resolve a critical alert that hasn't even been acknowledged, right? This ensures data integrity and prevents miscommunication. For example, acknowledged alerts can't revert to new status without explicit escalation rules. Our system also includes smart state management. Critical alerts require manual acknowledgement within 15 minutes or they auto-escalate. High-priority alerts auto-acknowledge after an hour if conditions improve, while medium and low-priority alerts auto-resolve after sustained recovery periods. This layered approach ensures that the right alerts get the right attention at the right time. Moving beyond rigid, static thresholds is key to truly intelligent alerting. Our smart severity classification engine considers multiple factors to accurately prioritize issues. It looks at the impact scope, how many users or services are affected. It considers historical context. Is this a known transient issue or something new? Time sensitivity is also crucial. An alert during business hours might be critical, while the same alert during a maintenance window might be a low priority. And finally, dependency chains are factored in. A database alert will automatically elevate dependent service alerts, anticipating cascading failures. Complying with this is our auto-resolution intelligence. This engine prevents alert storms while maintaining reliability. It monitors for sustained recovery, waiting for conditions to normalize for double the original threshold period before auto-resolving an alert. It's also dependency-aware, meaning it won't resolve upstream alerts until all downstream issues have cleared. And importantly, it incorporates business logic, respecting maintenance windows and scheduled deployments. This prevents unnecessary alerts during planned activities, allowing your team to focus on genuine, unexpected problems. When an engineer acknowledges an alert, our system doesn't just change its status. It records the acknowledgement timestamp and engineer identity, sends notifications to relevant teams, and importantly, starts SLA timers for resolution. It can even aggregate related alerts under the same incident, streamlining the response. But the value doesn't stop at resolution. Every state change, acknowledgement, and resolution is meticulously recorded, creating a complete alert history. This history includes precise timestamps, responsible parties, context about the trigger, and metrics like time to acknowledge and time to resolve. This invaluable data allows you to identify noisy alert rules, understand team response patterns, calculate true system reliability, and reconstruct post-incident timelines for thorough analysis. For production environments, scalability and reliability are paramount. Our design incorporates event sourcing, treating every state change as an immutable event for perfect audit trails and time travel debugging. Idempotent operations ensure duplicate alerts or acknowledgements don't create inconsistent states. And circuit breakers protect against cascading failures, ensuring alerts are still processed and stored locally even if external notification systems fail. By now, you should have a solid understanding of how to build an intelligent alert processing pipeline. As a final self-assessment, consider how does intelligent alert processing reduce operational overhead and improve system reliability? Reflect on this and you'll solidify your grasp of this critical topic. Thank you.